Shout out to Uzali. Link will be in the description.
Hello everybody, welcome back to our Gregorius math video. In this video, I'm going to be proving the functional equation for the Riemann C function. And just recall from last video that C of z is 1/2 z times z minus 1 gamma of z over 2 pi to the negative z over 2 zeta of z. Okay? And the functional equation, which allows us to analytically continue this to all of the complex plane, is the following. So C of z is equal to C of 1 minus z. Okay? This is what we're proving. Okay? And the proof is as follows. I'm going to be using the result I proved in number 3 2.1. That was the whole point of the video. I was planning to do this a lot quicker, but I kind of forgot to do it. Let's see if I can remember how to do this. So, if we have gamma of z over 2, what we're going to do is we're just going to write out the definition, and then with a slightly counterintuitive substitution, we should be on track to doing this. Okay, so gamma of z over 2 is equal to the integral between 0 and infinity of e to the negative t to z over 2. Okay, this is the definition. Now, letting t equal pi n squared u implies that dt equals pi n squared du. Now the boundaries don't change, and we're going to get that this equals the integral between 0 and infinity of e to the negative t, sorry not t, e to the negative pi n squared u, pi n squared u to the z over 2 minus 1 times dt, which is pi n squared du. Okay, now some of the stuff will cancel and we'll move some of the other stuff to the other side. So, if we have pi n squared to the z over 2 minus 1 times pi n squared, we get pi n squared to the z over 2. Then we move, because that's constant, because those are constants, we can move them to the other side. Pi to the z over 2, moving it to the other side, will become pi to the negative z over 2. And n squared to the z over 2 is just n to the z. So moving it to the other side, we'll get n to the negative z. So we get gamma of z over 2, n to the negative z, pi to the negative z over 2, equals the integral between 0 and infinity of e to the negative pi n squared u times u to the z over 2 minus 1 du. Okay, so this is what we end up with. Now, we've got our pi to the negative z over 2, pi to the negative z over 2, gamma of z over 2, gamma of z over 2, and we have an n to the negative z. But remember that the sum from n equals 1 to infinity of n to the negative z equals zeta of z. Yes, okay, fine, I'll put the extra bracket, okay? Okay, and so we can just take the sum from n equals 1 to infinity on both sides. Because we don't have n here or here, we could just bring those outside the sum, okay? So actually, we're left with gamma of z over 2, zeta of z, pi to the negative z over 2 equals the integral between 0 and infinity of psi of u to the z over 2 minus 1 du. And this right here is not a function like that we study at all, but I'm just doing this for convenience. This is not a function that's been studied much, of e to the negative pi n squared u. But a function that has been studied is the something theta function, which I looked at all the way back in number 3 2.1. And from there, and using the fact that sum from n equals negative infinity to infinity. Well, because we have an n squared here, that's equal to 2 times the sum from n equals 0 to infinity, which is just equal to the sum from n equals 1 to infinity plus the sum from n plus the point where it's 0 plus the sum from n equals 1 to infinity. Okay, and then we do some simple algebra from the result that I got last time in order to conclude that c of u to the negative 1 equals square root of u c of u, okay, plus 1/2 square root of u minus 1/2. Okay, so we get this. This follows very easily as soon as you watch number theory 2.1. Okay, that follows easily. So actually we're just left with this right now, and this, we're just going to focus on this integral here. This equals the integral between 1 and infinity of c of u to the z over 2 minus 1 du, plus the integral between 0 and 1 of c of u to the z over 2 minus 1 du. Okay, and now this right here, this is a step which I wouldn't think of doing, but actually makes a lot of sense after we do the substitution v to the negative 1 equals u. This means that negative v to the negative 2 dv equals du. Okay, and this also means that u to the negative 1 equals v. Okay, so here we're going to have this equals the integral between 1 and infinity of c of u to the z over 2 minus 1 du, plus the integral between infinity and 1. Well, I'm going to use a minus sign to change the bounds. But look, we have a minus right here, so that becomes a plus. So we're going to get c of v to the negative 1. And then this here, right here, will become minus z over 2 plus 1. So we're going to get v to the minus z over 2 plus 1 times v to the negative 2 dv. Okay, and I'm just going to rub this out now. And now we can proceed from here by expanding this out. So this equals, and I'm going to rub this out too because we all know what this is now. I'm going to say that this equals the integral between 1 and infinity of c of u to the z over 2 minus 1, yep, du, plus the integral between 1 and infinity of, now we expand this out with that formula over there, and we're going to combine the powers here. Minus 2 plus 1 is minus 1, so we're going to get square root of v, c of v, plus 1/2 square root of v minus 1/2. Okay, and then this times v to the negative z over 2 minus 1 dv. Yeah, okay. And now, I'm going to distribute this in and then combine the integrals together because they have the same bounds. So doing all of this leaves us with the integral between 1 and infinity of c of u to the z over 2 minus 1 du, plus the integral between 1 and infinity of, this times this, minus 1 plus 1/2 is minus 1/2, so we're going to get v to the negative z over 2 minus 1/2 c of v plus 1/2, and again we're going to get v to the negative z over 2 minus 1/2 minus 1/2 v to the negative z over 2 minus 1 dv. And now, same bounds, we can combine the integrals to, well, actually we're not going to combine it into one, we're just going to mix and match, kind of. So this equals the integral between 1 and infinity of, and also we're just going to let u equal v, because it doesn't matter. If we change the v to a u, all of the v's to u's, then we're going to get the same thing. So this is c of u times, Well, which terms here have a c of u? Well, we have u to the z over 2 minus 1. And then we have this as well, plus u to the negative z over 2 minus a half. Du plus the integral between 1 and infinity. And actually, we're going to factor out half of this minus this. Of u to the negative z over 2 minus a half minus u to the negative z over 2 minus 1 du. Now, this equals right here the integral between 1 and infinity of c of u times u to the z over 2 minus 1 plus u to the negative z over 2 minus a half du plus 1/2 times, well, this is just a simple u substitution. Not u substitution, a power rule. Okay? And, okay, and, if you do the power rule here, you should end up with, if I've done this correctly, 1 over z times z minus 1. Okay? I'll tell you in the comments below if I've done this correctly. But this is just a simple power rule. Okay? Now, here, actually we don't need to do anything more, actually. Because right here, if we change a z to a 1 minus z, nothing changes. And hence, this completes the proof. And actually, this fact right here, well, a corollary is that if we have the real part of z equal to a half, okay, we get this fact. And this is very, like, you know, something's definitely going on in the critical line here. There's some symmetry, there's gammas and zetas and symmetry here. Something is going on, okay? This is just a very interesting fact, using the beautiful underlying symmetry between the gamma and the zeta function. But yeah, that's it for this video, and hopefully you enjoyed. I'll see you in the next video. Bye.